If I have a uniform charge to mass ratio, and I run these, and I try to do electrophoresis in solution, is that going to work? Am I going to be able to separate my proteins in solution if they're all the same shape and they have a uniform charge to mass ratio? They're all drawn out lines like that? Not very well, right? Because as long as they have the same charge to mass ratio, they're going to move at about the same rate of speed. So clearly, I need something better than just liquid to do this in. I have to have a sieve, some way that the longer molecules are going to take longer to get through than the smaller molecules, even though they have the same charge to mass ratio. I need a molecular sieve. Who doesn't know what a sieve is? Raise your hands. All right, a sieve is like a strainer, right? So I need some sort of a molecular strainer that's going to let the small molecules through faster than it lets the large molecules through. And the way I'm going to make this molecular sieve is a gel. And I'm going to make my gel out of polyacrylamide. Okay? So we're going to call this a polyacrylamide gel. How do I make this polyacrylamide gel? So we're going to make a polyacrylamide gel, and to do that I have to remind you what acrylamide is. Acrylamide is this. Okay? It's two carbons double bonded with an amide stuck on one end of these, okay? This is acrylamide. And if I do this in the presence of persulfate, which is S2O8, S2O8, it's an oxygen, 2 minus, this disproportionates into SO4 minus dot, okay? And I do this in the presence of an accelerator, something called TMed, that's an accelerator. What happens is I end up with a molecule that looks like this, CH2. That sulfate radical that you see here, from persulfate that disproportionated into SO4 minus dot, okay? That radical steals one of the electrons from this double bond. So now I have an unsatisfied bond here with a radical. What do you think this is going to do? It's going to steal an electron from a neighboring acrylamide bond. And then I'm going to end up, when it does this, with this, CH2, CH, CONH2, CH2, CH, CONH2, and I have another unsatisfied bond. Okay? What is that unsatisfied bond going to do? Same thing. It's going to steal another electron from another acrylamide molecule, and this is going to keep going on and on and on. Raise your hand if you're class 10, or I'm sorry, if you're course 10 or course 3. What do we call this reaction? We do it with nylon all the time. What's it called? Radical polymerization, right? Now, what's going to happen at the end of this, right? Am I going to make a gel? No. I'm going to make a long polymer like nylon. I'm not going to make a gel. If I want to make a gel, I have to have some way for these long radical chains that I'm going to grow, that are going to grow like this, to be cross-linked to each other. So I need a cross-linker. And that cross-linker that I'm going to add is called bisacrylamide, which stands for methylene bisacrylamide. And what that looks like is this. Okay? So you can see that what I have here is one acrylamide molecule shown here and another acrylamide molecule shown here that are linked together by this methylene bridge. Why is this going to work as a cross-linker? Because once I get radical polymerization started, I'm going to build a chain here, right? And another radical reaction might form a chain over here. And now these two chains are linked together by this bisacrylamide. So the end result of this is going to be I'm going to have one chain like this and another chain like that and a cross-link in there. And that if I continue doing this, dot, 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 I will eventually end up with a whole long series of molecules all linked together in some type of chain structure. And this gives me my gel. Now, what we typically do, as I suspect many of you are aware, is we pour this gel between two glass plates. So I have a thin slab of gel, and now I'm going to apply a negative charge here and a positive charge here. Why do I put the positive charge at the bottom? What charge are all of my proteins from the SDS? Negative. So they're all going to try to move their way through that gel. And you can see that as they try to go through this sieve, this strainer, this gel, the small molecules are going to be able to run pretty quickly, whereas the larger molecules are going to have a hard time and they're going to take longer to go through. So as I run this gel as a function of time, the smaller molecules move fast and the intermediate ones move in intermediately and the bigger ones move slower. So I can separate all these molecules now based entirely on their size or their molecular weight. Okay? What do I do after I run this gel? How do I see the proteins in the gel? I mean, the proteins are, right? You can't see, most proteins at least, you can't really see. So how am I going to see them? Think back, what did we talk about earlier? How did I measure protein concentration? Dye, right? I'm going to add a dye. So I'm going to stain the gel with a dye. What dye do you think I should use? Kumasi blue. Okay? So I have two choices here. I can use Kumasi blue, which isn't a bad way to go. Kumasi blue, if you use it, will let you detect up to, detects up to about 0.1 micrograms of protein. So that's about the minimum I can have in a band to typically see it. Another way I can do this is I can use something called a silver stain. Turns out that proteins will react with silver. So I can do a series of reactions to make the protein reactive and add silver. And now when I look at my gel, the gel will have color based on where the silver reacted with the protein. And this lets you detect as little as 0.02 micrograms, right? Which is about 20, or is exactly 20 nanograms of protein. So silver staining is what you want to use when you don't have a lot of protein.